All right, now let's have a look at part B of topic 12. So in the second part of topic 12, we'll have a look at the concept of angles inside and outside circles, and then tangents, and we'll tackle some more related problems. Okay, first let's have a look at a introductory example. Okay, a line that intersects a circle in 2 points is called a secant. In the second part, we'll explore relationships between the angles formed by intersecting secants and the arcs of circles these angles cut off. So first, let's consider this question here. I'll give you 2 minutes to have a look at this question, and then we'll have a look at the solution together, okay? So given that AB is 40 degrees, or there's a typo here, this should be arc AB, and also arc CD is 80 degrees, can you find angle AEB? And if you finish, please give your answer in the chat box, okay? You can try to prove what we just learned about inscribed angles. Okay, let's have a look at the solution together. So for example, we could connect points A and D, right? In that case, we have created some inscribed angles. We have angle BAC equals 1/2 the corresponding arc CD, right? And this gives us 40 degrees. And on the other hand, we have angle ADB equals 1/2 of the corresponding arc, which is AB, and this gives us 20 degrees, right? You get it? Therefore, we have angle AED is 180 degrees minus angle EAD minus angle EDA. And that gives us 120 degrees, right? And therefore we have angle AEB is just 180 degrees minus angle AED, which is 60 degrees. Did you get it? Okay, so let me ask you another example. Suppose the measurement of AB is x and the measure of CD is y. Are you able to express this angle in terms of x and y? That's a connection of that angle with the corresponding arc AB and CD. So basically there's another question here. If chords QS and PR intersect at T, so suppose we have a circle, chord QS and PR intersect at some point T here. Given that the measure of RQR equals X, and the measure of PS equals Y. Can you find a formula for angle QTR in terms of X and Y? So the method should be the same with the previous one, right? Again, we could make use of some inscribed angles there. For example, we could connect points P and Q, right? Since angle QPR is inscribed in arc QR, we have angle QPR equals half of X, right? Similarly, we also have angle PQS equals a half of Y, right? And angle QTR is actually the exterior angle of PQT, of triangle PQT, right? That means we have angle QTR equals angle PQT plus angle QPT, which is X plus Y over 2. Did you get it? So that brings us a very important feature of intersecting chords, which you should remember here. The measure of the angles formed by two intersecting chords is the average of the measures of the arcs intersected by the chords. For example, in the diagram at right, we have angle PTS equals angle QTR, which equals X plus arc PS plus arc QR over 2, which equals X plus Y over 2, that diagram. Okay, note here, T is not necessarily the center of that circle, okay? T could be any point inside that circle. As long as it's the point of intersection of the two chords, you always have this relationship here. Okay, please write this down, and we're going to use this to solve some example questions below, okay? Alright, have we finished? Okay, then we have a look at the point of intersection inside the circle. Now let's have a look at when the point of the intersection of the two chords is outside circle, what will happen? So here we are given a diagram. The measure of arc D is 110 degrees and arc BC is 20 degrees. Can you find angle DAE? Which basically means if you know this arc, if you know this arc, then you can express this angle in terms of these two arcs. Again, if you finish, please give me an answer in the chat box, okay? Alright, have you finished? Not that difficult, right? So we could also make use of some inscribed angles here. For example, we could connect the point B and E, right? Therefore, in that case, we have angle BEC should equal a half of arc BC, right? Which is 10 degrees. And also, the angle here, okay, first of all, we know this angle is 10 degrees. And the angle DBE is inscribed in the arc DE, right? So that equals 1/2 of the corresponding arc DE, which is 55 degrees. And also, if you consider triangle ABE, this angle here, DBE, is external angle of the angle A and angle AEB, right? Therefore, we have angle A is just angle DBE subtracted by the other angle BEC, and that gives us 45 degrees, right? So this angle here, the desired angle, is 45 degrees. Did you get it? Also, we could generalize this problem by letting BC equals X and DE equals Y, and find the expression of angle A using X and Y, right? For example, if we generalize this problem like this, give it a circle like in the diagram here, XV, the measure of arc XV equals B, the measure of arc YW equals A. Again, be careful, these are arc measures, not lengths, so they are degree measurement. In the diagram, we can prove actually angle Z equals B minus A over 2, right? So the method should be the same. We can connect these 2 points, Y and V here. And first of all, we could calculate this angle here, which is A over 2, right? Because this angle is inscribed in the arc YW. And of course, this angle here is inscribed in arc XV. So that angle here is B over 2, right? And then this angle here is B over 2 minus the other angle here, A over 2, because angle XYV is the external angle of triangle VYZ of the angle Z and angle YVZ, right? Therefore, we have proved angle Z equals B minus A over 2. Did you get it? Okay, so again, this brings us another important feature. If we have two seconds that meet at a point outside the circle from an angle equal to half the difference of the arcs they intercept, for example, in the diagram on the right, then we have angle Z equals B subtracted by A over 2. Okay, please write this down in a notebook. And again, next we'll use what we have learned so far to solve some example questions, okay? All right, next let's have a look at some questions. Okay, first example, given that arc AB is 40 degrees, arc AB is 120 degrees, arc DC is 100 degrees, can you find the angle BPC and angle BEC? Again, if you finish, please give me an answer in chat box, okay? 40 degrees, 120 degrees, 100 degrees. Okay, let's have a look at the solution together. So according to what we have learned here, if you want to find this angle here, you need to know this arc and this arc, right? AD is already given to you, so the key to find angle BEC is to find arc BC. So first of all, arc BC is 360 degrees, subtracted by arc AD and arc CD and arc AB, right? And this gives us 100 degrees here. Therefore, we have, first of all, angle BEC equals arc BC plus arc AD over 2, right? Remember this? In that property here. So that gives us 70 degrees. And then angle BPC equals the difference between these two arcs over 2, right? And that gives us 30 degrees. You get it? It's very straightforward question, right? So far in this lesson, we have only learned these two properties. Okay, any questions here? If not, let's consider another example. Again, using what we have learned so far. In this figure, angle Y equals 58 degrees, angle W equals 20 degrees, segment XZ is perpendicular to segment WX. Can you find angle WOV and angle VXV? So angle V is this angle here. Oh, sorry. Angle WOV is this angle here. VXV is angle here. Find these two angles. All right, let's have a look at the solution together. I hope you can finish by yourself, okay? Okay, first consider the angle WOV. So WOV is this angle here. In order to find that angle, we need this arc here and this arc here, right? Because this is a point of intersection between these two chords, XV and WZ. So that basically is 1/2 of the sum of these two arcs. Okay. Because we have angle XWZ equals 20 degrees, we know that arc XZ must equal twice of that angle, right? Which gives us 40 degrees. And because angle Y equals the difference between the arc WV and arc XZ divided by 2, we then have 58 degrees equals WV minus XZ is 40 degrees, right? Over 2. So that can solve arc WV is 156 degrees, right? Therefore, we have the two crucial measure of arc XZ and arc WV. So WV here is 156, XZ here is 40, right? So that means we can find angle WOV. WOV is point of intersection between the two chords, so angle WOA should equal 1/2 of the sum of the two corresponding arcs, which is WV plus the arc XZ, right? And this gives us 1/2 of 156 degrees plus 40 degrees, and that gives us 90 degrees. That's a measure of angle WOV, right? Okay, next let's consider the angle ZXV. So we can use arc VZ here to find the angle ZXY, right? So angle ZXY is basically half of the corresponding arc because it's inscribed in the arc ZV. So we focus on the arc ZV since we know that the arc WVZ equals twice of the angle ZXW, which is 180 degrees. We have the arc VZ equals 180 degrees minus the measure of arc WV, and that gives us 24 degrees, right? Well, this arc here is 24 degrees. And therefore we know angle ZXY is simply half of the arc VZ, which gives us 12 degrees. Did you get it? Any questions? Okay, if you don't have any questions, let's take a 10 minutes break. Let's return before 35 past 8, okay? And next we'll have a look at the other two concepts, tangents, and some more related problems. So the proof we have just see here tells us very important feature. Line tangent to the circle is perpendicular to the radius drawn to the point of tangency. Conversely, a line drawn through a point on a circle that is perpendicular to that radius drawn to that point must be tangent to the circle. For example, for the diagram at right, we can write line BC is perpendicular to radius OB if and only if line BC is tangent to circle O. Also recall, this symbol here means if and only if, which means these two statements are equivalent. All right? Okay, so please write this down on your notebook, and we're going to use this to solve a series of example questions later. All right, have we finished? Okay, let's see another example here. Line M is tangent to a circle at point A, given point B on the circle, such that arc AB is 80 degrees. Can you find the acute angle formed by chord AB at line M? So I draw the diagram for you here. We have a circle, and line M is tangent to the circle point at point A. So this is line M. Given point B on the circle such that AB is 80 degrees, can you find the acute angle formed by chord AB and line M? So we are trying to find this circle here. I'll give you 1 minute to think about this question, okay? And then we'll have a look at the solution together. Using what we have just learned here, we have already proved this property, so you can just use it directly, right? So if you have a tangent line here, that means we could make use of some perpendicular lines, right? I'll give a hint. So we could start by drawing the diameter AC. Then we have a 90 degrees here, right? Since we know this line is perpendicular to M at point A, and since arc AC is a semicircle, we have BC equals 180 minus arc AC, which is 100 degrees, right? So if you know the measure of the arc, of course you can find the angle inscribed in that arc. Therefore, we have angle BAC equals 1/2 of that corresponding arc, which gives us 50 degrees, right? So let's call another point Z here. Then of course you know angle DAB equals angle VAC minus angle BAC, which equals 90 degrees minus 50 degrees, and that leaves us 40 degrees, right? Did you get it? And actually, you notice that angle ZAB here is 40 degrees, which is 1/2 of the arc AB, which is 80 degrees, right? So that means if you are given, if we generalize this question as angle AB is x, then you could use the same method to find the angle VAB, which should be x over 2, right? Again, this gives us another important property here. An angle formed by a tangent and a chord with the point of tangency as the endpoint equals 1/2 of the arc intercepted by the angles. For example, in the figure at right, line M is tangent to the circle at A, which means it only passes through the circle once at point A. So here, this angle ZAB equals 1/2 of the measure of the arc AB. So if AB equals x in degree measurement, then this angle is simply x over 2. Did you get it? Again, please write this down in a notebook. This is another important property, okay? And also, an angle between a tangent and a chord is also often referred as a inscribed angle. This is the same name we give to an angle between two chords that share endpoint. Measures of both types of angles equal half the measures of the arc they cut off. So this angle here is also called inscribed angle. Because it also equals half of the corresponding arc, right? Which means this angle. So if you have another point here, well, let's call it D. So this angle equals this angle. Both of them are called inscribed angle of arc AB. You get it? Okay, let me know if you finish, alright? Alright, good. So now we turn to angles formed by a tangent and a secant. So now let's consider another problem. In this diagram, arc BD is 110 degrees. Arc BC is 40 degrees. Line AB is tangent to the circle at point B. Can you find the angle of BAD here? So we have already learned a very similar question before, right? So if A is a intersection point between two chords like this, we know this angle should equal 1/2 of the difference between this arc and this arc, right? So here the situation is pretty similar, except we don't have two chords but a tangent line here. But the method should also be the same. So we could connect point B and D to help us solve this problem, right? So in that case, we have angle BDC equals arc BC over 2. Did you get it? BCD is here. Oh, sorry, BDC. BDC is here. That's 1/2 of the arc BC, which is 20 degrees, right? And we also have angle XBD. So let's call X is some point on the line here. Angle XBD is also a inscribed angle of the arc BD, right? So that's 1/2 of the arc BD, which gives us 55 degrees, right? And we know that angle XBD is the exterior angle of triangle ABD. So that leaves us this angle is angle BAD is simply the exterior angle XBD subtracted by angle BDC, and that's 55 degrees minus 20 degrees, which gives us 35 degrees, right? Did you get it? And again, we can also generalize this question by letting BD equals X and BC equals Y. So angle A here is, using the same method, we can prove that angle A here equals X minus Y over 2. Did you get it? So this have a similar form of what we have learned in previous property here. So if you have 2 seconds meet a point outside the circle, then angle Z here equals B minus A over 2, right? And this time we have a tangent and a secant. The conclusion is very similar. We have this property here. Again, please write this down in a notebook. The angle formed by a tangent and a secant is half of the difference of the intercepted arcs. For example, in the diagram on the right, we have angle BAD equals arc BD subtracted by arc BC over 2. Unsurprisingly, the angle formed by a tangent and a secant has the same relationship to the arcs the angle intercepts as the angle formed by 2 secants does, right? Any questions? Okay, let me know if you finish, alright? Okay, then let's consider another question. Segments PA and PB are tangent to the same circle at A and B, respectively. Can you prove that PA equals PB and that angle APB equals half of the difference of major arc AB and minor arc AB? Okay, again, let's draw a circle here. We have PA, so P is here. We have a PA touches the circle only once. PB touches the circle only once here. Can you prove PA equals PB and APB equals half of the difference of major arc AB and minor arc AB? Any ideas? Suppose this is a center point of that circle. Okay, I'll lead you through this example, okay? So we can start by drawing the ready to the points of tangency, thus forming 2 right angles. So if you connect A and O and B and O, then these 2 angles must be 90 degrees, right? We also draw PO. To complete a pair of right triangles, since we have AO equals BO, we have triangle OAP is congruent to triangle OBP by HL, right? Because they are 2 right triangles. Hypotenuse and a pair of sides. That means these 2 triangles are congruent to each other. Therefore, we have PA equals PB. This proves PA equals PB, right? And now we can find angle APB in a variety of ways. One of the methods is to use quadrilateral PAOB. To note that angle APB equals 360 degrees minus angle PAO minus angle AOB, both of them are 90 degrees, then minus angle OBP, right? and that leaves us 180 degrees minus angle O OBP. Angle OBP is, oh sorry, that should be angle AOB, because angle OAP is simply 90 degrees. Okay, and we know that angle AOB is the central angle corresponding to arc AB, so that equals 180 minus arc AYB, right? So let's suppose there's a point Y here to denote the shorter arc. We use another point to denote the longer arc. Since we know that the arc AXB equals 360 degrees minus the arc AYB, we also have the arc AXB minus the arc AYB over 2 should equal 360 degrees minus 2AYB over 2, which gives us 180 degrees minus arc AYB, right? This is exactly the same with the expression of the angle ABP. Thus, we have proved angle APB equals 1/2 of the difference of the two arcs, AXB and AYB. Did you get it? Okay, and this is you can also treat this as another property. So as shown here in this diagram at right, we can draw two tangent segments to a circle from the point outside the circle. Then these tangents are always equal to each other in length. All right. And also, we have also proved that this angle here, angle P, can be expressed as, well, suppose this is point X, this is point Y. Angle P can be expressed as 1/2 of arc AXB minus arc AYB. The difference between the longer one and the shorter one, right? All right, any questions? So the information about the angle between the tangents is unsurprising, as it's essentially the same as the angle between two secants, right? Can you connect them? This is a case of two tangents. This is a case of one tangent and one secant. And this is a case of two secants. Actually, they are very similar, right? However, the information about two tangents from the same point is new. Here, if we have two tangents like this, we can always have PA equals PB. Alright, so now let's use what we have learned so far to solve this problem here. Oh, sorry, this one here. Any ideas? Point P is 12 centimeters from the center. O of a circle with radius 10 centimeters. Point Q is on the circle such that PQ is a tangent to that circle. Okay, let's draw the diagram. And you have a circle and a tangent line, right? So this is point O, which is center of that circle, a point P, and another point Q. So we need to find the length of PQ, right? again, let me lead you through this. We can start by drawing a radius, because once you have a line tangent to a circle, usually we'll want to make use of some perpendicular lines, right? If PQ is tangent to that circle, we know that QO is the radius, and then this angle here must be 90 degrees, right? Then we could connect PO, that gives us a right triangle. So if P is 25 centimeters from the center, that means PO equals 25, right? And radius 10 means QO is 10. Of course, we can find PQ in that right triangle, right? So PQ is just square root of PO squared subtracted by OQ squared, right? So this gives us 225 minus 100. And that leaves us 5 square root of 21 centimeters. Did you get it? Any questions? Okay, then if no questions, let's have a look at more related problems to angles inside and outside of circle. So let's consider this question here. A quadrilateral is said to be cyclic quadrilateral if a circle can be drawn that passes through all 4 of its vertices. Can you prove that if ABCD is a cyclic quadrilateral, then angle A plus angle C is 180 degrees? So ABCD is cyclic quadrilateral, that means all of its vertices are on a circle, right? So let's draw this situation here. Suppose these are the 4 points. Can you prove angle A plus angle C equals 180 degrees? So note that angle A is the inscribed angle of the arc, the longer arc DCB here, right? You see that? And angle C is also an inscribed angle of this arc. And actually sum of these 2 arcs equals 360, right? And we know inscribed angles are just 1/2 of the corresponding arc. So we could prove this like that. We have angle A plus angle C is 1/2 of arc BCD plus 1/2 of the arc BAD, right? This leaves us 1/2 of arc BCD plus arc BAD, and then we know the sum of these 2 arcs is just 360 degrees, so that equals 180 degrees. Did you get it? Can you follow me? So actually you can also consider this as a special property for the cyclic quadrilateral, which states that quadrilateral is a cyclic quadrilateral if a circle can be drawn that passes through all 4 of its vertices. Such a quadrilateral is said to be inscribed in a circle. Opponent angles of any cyclic quadrilateral sum to 180 degrees. We have already proved this, right? Okay, so have a look at this property here. Any questions, just let me know, okay? And if you don't have any questions, let's consider another example. So consider the figure on the right. Segment PC is tangent to the circle, and segment PD bisects angle CPE. If arc CD is 70 degrees, arc DE is 50 degrees, and angle DQE is 40 degrees. Can you determine the measure of the arc from A to E that does not include point C, which is a short arc here, right? Okay, I'll give you 1 minute to think about this question, and then we'll have a look at the solution together. If you have finished, please give me your answer in the chat box. Okay. Let's have a look at the solution together. So you want to find the measure of this shorter arc here, right? We know the whole circle is 360 degrees. We know this section CD, which is 70 degrees. We also know D is 50 degrees. So if you can find this arc and this arc, then using 360 minus this part, this part, this part, and this part, that'll give us the measure of AE, right? So first of all, let's see if we can find the measure of BC. First, we note that since angle DQE equals 1/2 of Q is the intersection between CE and BD, right? Then we know DQE must equal 1/2 of DE plus CB, right? So this means angle DQE is 40 degrees equals 1/2 of D is 50 degrees plus CB. So this gives us the measure of arc CB, right? Which is 30 degrees. So that solves one of the arcs we need. And now we have CB, we could find angle CPD, right? Note that angle CPD just equals 1/2 of arc CD minus arc CB, and this is 20 degrees, right? If CPD is 20 degrees, since DP bisects angle CPE, we know that angle DPE is also 20 degrees, right? Because angle DPE also equals 1/2 of arc DE minus arc AB. So that tells us that 20 degrees equals 1/2 of DE is 50 degrees minus arc AB. And we can find arc AB is actually 10 degrees, right? Therefore, we have the shorter arc AE should equal 360 degrees minus the arc CD minus the arc DE, arc CB, and arc AB, right? And we know all of these arcs, so eventually that gives us a shorter AE equals 200 degrees. Did you get it? Okay, then if you don't have any question, let's consider another question. Median AM of triangle ABC has length 8. Given that BC is 16, AB is 9. Can you find the area of triangle ABC? Okay, again, let's draw the diagram here. Median AM, we have a median here, AM has length 8, given that BC equals 16. AB equals 9. What is the area of triangle ABC? Okay, so basically we know BM is 8 and MC is also 8, right? Because M is the midpoint of BC. Any ideas? Okay, let's have a look at the solution together. So when we draw the figure and label all of our lengths, we see that BM equals MC equals AM, right? Therefore, if you centered at point M using 8 as the radius, we could actually draw a circle like this, right? A circle centered at M with radius 8 goes through all 3 vertices of triangle ABC. You see that? Then BC is actually the diameter of that circle. So we immediately know this angle here is 90 degrees, right? Because this angle is inscribed by half of the circle. Therefore, we know we could find AC first. AC equals square root of BC squared minus AB squared, and this gives us 5 square root 7. Therefore, the area of triangle ABC is 1/2 of AB times AC, and this gives us 1/2 of 9 times 5 square root 7. Did you get it? And this actually tells us one important property. If the length of a median of a triangle is half the length of the side to which it's drawn, the triangle must be a right triangle, right? Moreover, the side to which this median is drawn is the hypotenuse of the right triangle. Did you get it? Any questions? Alright, then let's consider another problem. So if we let Z be a point where the inner circle of triangle ABC meets segment AB, can you find AZ in terms of the size of triangle ABC? So basically we have a inscribed circle. Then let's draw the corresponding triangle. So these are the points of tendency. Let's call them X, Y, and Z. Okay, so can you express the length of AZ here, this length? in terms of the size of triangle ABC. Okay, let me lead you through this example. All right, so in order to facilitate our discussion, we could label the equal tangents from the vertices like this. So if we let AZ equals X, then AY must also equal X, right? Because AZ and AY are tangents of the circle. And if we label BZ equals Y, then we know this length BX is also Y. YC, if we label that as letter C, then XC also equals Z, right? Sorry, Z, not C. Then actually we want to relate X to the size of the triangle. So we write the size of the triangle in terms of X, Y, and Z. We let the size of the triangle be AB equals C, AC equals B, and let BC equals A. Then we have AB equals C equals X plus Y, right? And AC equals B, which equals X plus Z. And BC equals A, which is Y plus Z, right? We want X in terms of A, B, and C. So adding the three equations could help us with this. So add them up. Will give us X plus Y plus Z, which we can use with Y plus Z equals A to find X, right? So on the right side, we have X plus Y plus Z. On the left side, we have A plus B plus C. Oh, actually, the right side is twice of X plus Y plus Z, right? And then we have X plus Y plus Z equals a half of A plus B plus C, right? Then because we want to find X, so we need to eliminate Y plus Z, right? So let's call this equation number 4. So then we could use equation number 4 subtracted by equation number 3. And the left side just becomes X. The right side is 1 over 2 A plus B plus C minus A, right? And if we let, well, usually we'll use letter S to denote half of the parameter of triangle ABC, right? If we let S equals 1/2 of A plus B plus C, then we know that X equals S minus A. Did you get it? Where S is semi-parameter, or half the parameter of the triangle. So this actually gives us a relationship between X and A. Also, similarly, you can use the same method to show that Y equals S minus B, and Z is actually S minus C. Did you get it? This is a relationship between X1, Z, and ABC. So again, you can treat this as an important property, which states that the length from the vertices of triangle ABC to the points of tangency of its incircle are given as follows. So if you have a diagram on the right, then we have length of AZ equals AY, which is S minus A. BZ equals BX equals S minus B. And CX equals CY, which is S minus C. where AB equals C, AC equals B, and BC equals A. And the semi-perimeter of triangle ABC is S. Okay, please write this down on your notebook. And in your homework, you'll find similar questions using this property. All right, so because we're running out of time, I'll leave 2 additional questions for you to complete as a homework, okay? So please copy these 2 questions here as part of the homework. This is the first question. And this is the second question. All right, you could also find some more practice questions in the homework of on Google Classroom. Okay, remember to complete your homework as much as possible, so we could discuss the questions in our next lesson. All right. All right. So this is the end of today's class. I'll see you next time. Bye.